Go.
Okay, go. All right.
Awesome.
So today we're talking about heat transfer. Okay, so we've got three types of heat transfer. We have conduction. So that's molecule to molecule transfer of energy. So we're going to start with that one, and then we'll work down the list. So I've got a little simulator to show us what that looks like. Let me get it going. That's kind of a cool simulator because it shows us conduction, but it also shows us thermal equilibrium. Right, what's thermal equilibrium? Anybody remember?
When everything's the same temperature?
Yeah, same temperature, exactly. So here we have two objects. The blue object is cold, the red object is warm, right? You can see the molecules moving a lot more here, right? We're going to bring them into thermal contact, and we're going to see heat flow, but we're going to see heat flow through conduction. And so that means molecule to molecule, one molecule is going to interact with its neighbor and transfer the heat that way. All right, so these molecules vibrating, when I bring this together, these molecules are going to interact with these, and that'll cause them to vibrate. And then what's going to happen? These are going to vibrate, right? And it's going to move down through the material. Does that make sense to everybody? And so we can see, watch that happen. Here we go. It's so exciting. So close, so close. And there we go. And so now you can see, right? These are now purple, right? And these are blue, because these are transferring, and then eventually it's all going to be kind of purple in the end, as I've transferred heat from molecule to molecule, transferring from the hot object into the cold object. Right? That's conduction. Make sense to everybody? All right. So we're close to thermal equilibrium. Let's reset it. And let's make the bottom really thin. So what's going to happen now?
The transfer faster.
And notice it's going to go, right? It got through it faster, right? Because it's thinner. If I make it very thick, the bottom, right? Then you can see it's taking longer to get through from the top to the bottom. So this kind of conduction, when we look at conduction, we're looking at the rate of heat transfer, not just how much heat, but how quickly it flows, right? And that depends on the thickness of the material, it appears, right? We're actually going to work out the formula for conduction. So let me get that up, write that up for you. Turn the projector off for a little bit. Then we'll turn it back on in a minute. Notes. Okay, here we go. So conduction. So let's imagine we have a material. Oh, wait, that's too big a material. Make it skinny. That's better. Like that. Try to draw in 3 dimensions here. That's not too bad, is it? That's not bad. Okay. L is the thickness of the material. A is the cross-sectional area of the material. We have one side and the other side at different temperatures. T2 is greater than T1 for simplicity. So we're going to say the left side is warm, the right side is cold. Right? Okay. And what's heat going to do? We'll do heat in red. What do you say? Red's a good color for heat. What's heat going to do? It's going to go from the hot side to the cold side. Right? This is not Monday morning, guys. Right? Heat's going to flow. Does that make sense to you? Right? Hot to cold. And we're looking at the rate of that heat transfer. So the power, which would be delta Q over delta T, right? How long it takes to flow through the material, okay? That's equal to a constant, capital K, the cross-sectional area of the object, the temperature difference between the two sides, divided by the thickness of the material. Okay, so the thicker the material, we saw that. The thicker the material, the longer it took the heat to transfer through, right? So the thickness is important. the area. The bigger the area, the more places I have the heat to get through the material. So it's proportional to that. Question?
Is that like power, the same power we were looking at earlier?
Yeah, which is energy per time. Yeah. So the units are what? If it's power, the units are going to be
Joules?
joules per second, right? Joules per second, which are
Watts.
watts. It's the same quantity when we did watts before. But here we're looking, instead of like a big object moving, we're looking at molecular motion. But it's the same quantity. Good question. Okay, K. K is called the thermal conductivity. And it depends on the material. All right, so the material determines, let's look at some values of K. So I think I have a table in the textbook.
What did you say A was?
A is across the area, cross-sectional area. So it's the direction the heat's flowing through the object. That's why it's on the side there. Okay, I'm gonna pull up a table of K's. I might have to erase something. Let's see. Okay. All right, this is good. All right, so this is our table. Oh, let's get rid of that. Okay, here's our table. Thermal conductivity, what are the units? Joules in the numerator, seconds, meters, degrees Celsius in the denominator. That'll work out to give me the right units. So those are the units for thermal conductivity. You can see metals, right? Aluminum, 238, copper, 397, silver, 427. Lead's pretty small for a metal, but it's, it's 34, right? So these are metals. Now look at the gases. What do you notice? What, Mary?
They're not conducting.
Yeah, it's very small, right? Why would a gas not be very conductive?
The molecules are farther apart.
Yeah, molecules are farther apart, and in transfer energy, one molecule has to hit another molecule. There's no connections between them. Right, so gas makes a good insulator. Right, anybody, your windows at home, they're two-pane, you know what I mean? Two-pane windows? You got one glass in the middle, air, right? To make it a better insulator. Right, because if it was solid glass, it wouldn't be as good. Right? You can go down and here you can see some interesting non-metals that have some interesting values, like asbestos. Wow, look at asbestos. It's pretty low. It's one of some gases. What's asbestos? Anybody know?
Stuff in walls.
Stuff in walls, ceilings, right? The old stuff they put in buildings. Why'd they put it in buildings? So, right, it causes cancer, it's bad for you. Everybody know what I'm talking about? Now they gotta wear masks and suits to get rid of it. Well, it was in there because, look at the thermal conductivity. It's a great insulator for cheap, easy to use material.
Is that like Chinese drywall?
Yeah, they put asbestos, right, because it was cheap.
Is that what it is?
Well, it's got asbestos in it.
Okay.
Not pure asbestos. Yeah. But it used to be in all the buildings.
I used to know a couple, the principal of my high school, her and her husband lived in a house in Chinese drywall when they first moved down here, and they still have very severe health issues.
Yeah. Asbestos is bad stuff. So.
Was it regulated though?
Yeah, but they, there was the whole,
But you still have people who bought those cheap houses,
yeah, and they
Like 30
imported
years ago?
stuff. Huh?
Is it 30 years ago?
No, this happened recently.
Like
So
20?
Oh, really?
asbestos got banned in like the 90s.
Ooh.
Yeah, my grandpa got like lung cancer from working on the ships.
Yeah, it's dangerous stuff. Great insulator. but dangerous
Great
stuff.
insulator.
We had it in the grade school. I remember just all along the pipes for carrying the hot water. So, yeah, scary stuff. All right, asbestos. Concrete, not bad. Glass is pretty good too. It's not as good as air, but you see, glass is a solid. Why is it got such a small value? That's weird. Anybody know why? Glass is pretty hard, right?
How you make glass? Is it related?
It's related to the structure of glass. Anybody know the structure of glass? Interesting. Glass doesn't form a crystalline structure. So even though it's like a solid, all the molecules are randomly placed in there. It's not like a nice array, like metal or something like that. So it doesn't have a nice structure. So that's why it has such a low value, because the molecules aren't all lined up nice and neat.
Somebody can see through it.
No, that's something else with the property. So,
Why can you see through it?
glass,
Yeah.
it doesn't interact with visible spectrum, but it interacts with like infrared. And we'll see that in a minute. So that's just a property of the electron bounding states. Because you can get plastic does that too. It's see-through. So okay, water, you can see different values. So this is thermal conductivity. Now we don't always want to conduct heat. Sometimes we want to stop the heat flow, right? We don't want to conduct. We want to be an insulator. So we want to see what that looks like in terms of the formula. So sometimes we're interested in insulating rather than conducting, and so we want to rearrange this formula. So I'm going to write this formula again. P equals Ka, there's an L here, and I'm just going to write delta T for shorthand. It's not truly a delta T. Don't get confused. What's delta T mean, really? Change. Final minus initial. But this is two different sides, left and right side. So it's really technically not a delta T. But it's easier to write delta T. You see what I'm saying? But it's not a final, it's not that temperature's changing with time here. It's just the left and the right. Okay? Over L. Okay, so I'm going to rearrange this and get delta T by itself. So if I do that, let me erase this, give us some space to work. So if I do that, I get P times L divided by K times A equals delta T. And now I'm going to group L, K over A and call that the thermal resistivity. You get the value R. This is THER. I think that's what. Right, the thermal resistivity. So P equals R, or P times R equals change in temperature. So this is when you want to talk about insulating power. Right? So R is proportional to 1 over K. So what that means, something that's a good insulator would be a bad what? Conductor. And something that's a good conductor would be a bad insulator, right? Because they're inverses of each other. Make sense, everybody? What's nice about doing the formula this way is imagine I have two objects, right, with different R's. So this is R1, this is R2, let's say T1, T2 in the middle, T3 on the outside. And in this case, I got heat flowing, let's say this way, Q, because T3 is greater than T2. T1, I just picked to go from left to right instead of right to left, but you get the idea. So heat's flowing through these two materials. So this morning it was cold out, right? 57, so what do? I put on a t-shirt, and then I put on a sweater, right? And so I'm doing this. I have one layer of material and another layer of material, right? I'm insulating. Does that make sense, everybody? So I want to look at the heat flow first from the outside here to the boundary, and then the boundary to the inside. Does that make sense? So if I look at my first heat flow, I would get P times R1, or sorry, yeah, R2. So from here to the boundary equals T3 minus T2. That's telling me the power flow of heat from the outside to the boundary, right? Basically, from out here to my sweater. Actually, it's going this way because I'm warm. So my t-shirt.
Yeah, quick question. So when you buy thermocloses, does it mean that they have a really high R, thermal resist,
Probably. But what do you mean by thermal clothes?
like the ones that you put
Yeah, like your
inside?
What do you mean?
Like thermal clothes for you to, let's say, hike a mountain.
Oh yeah, yeah, they're gonna have good resistivity. It'd be great if they were made of asbestos, but then it'd be bad for you. But it'd be great for heat, right? But yeah, that's the idea. Right, now I want to go from the boundary to the other side. So PR1 equals T2 minus T1. The same power flow, because whatever flows into the middle has to flow out through the other end. That's conservation of energy, right? Energy flows in, it's got to flow out. Right, so I got the same P. Well, if I add these, what do I get? PR2 plus PR1 equals, well, PR2 is T3 minus T2, and PR1 is T2 minus T1. What cancels on the right? What cancels on the right?
T2.
T2. You with me? And I can factor out a P on the left. So this here is my total, our total. The thermal resistivities just add. So when I put on a sweater, and I put on a t-shirt, and I put on a jacket, I just add the thermal resistivities to get the total resistivity. The total insulating power. Does that make sense, everybody? Thermal conductivities don't add. Right? Oh, yeah, here. Thermal conductivities don't add. You can't take one conductivity, add another conductivity, and get better. It doesn't work. Right? But does work for insulating. Okay, so that's thermal resistivity. Okay. All right, second one. We did this one. Done. Second one, convection. Large-scale motion of molecules from one location to another. All right, so we're not going molecule to molecule. We're taking molecules from one location, let's say they're hot or cold, but I'm transporting them to a new spot. All right, so that's how I'm transferring the energy or the heat. Can you guys think of any cases where that takes place? Where we have convection. Can you think of any convection systems? Anybody?
My oven at home.
Your oven at home is, I have a convection oven. Yeah, what does it do? Have you looked inside it?
No.
They should have a fan in there. And what's the fan do? It blows the air around. It moves the hot molecules from by the element to a new part of the oven. So it helps the oven heat more efficiently. All right, make sense to everybody? Like your air conditioner unit. Anybody got central air at home? You know what I mean?
Yep.
Yeah, you got the vent, it sucks the air out, then it blows out cold air right around the house. So it's creating a current. Or right out here along the ocean, along the beach. What's right out here off the coast of Florida? Anybody heard the Gulf Stream? What's the Gulf Stream?
Isn't just like air?
Not air, good try. It's actually water. It's warm water that comes up from the tropics, runs by Florida, that's why we're nice. And the rest of the country sucks in weather right now, right? And then it goes all the way up to England. Right? It's warm current flow. So you're taking warm air from the or warm water from the tropics and transporting it up north. Does that make sense to everybody? So we have large scale motion. I have a simulator for this, so let's look at it. But first let me erase the board. Okay, it's coming up. Slow, but it's working. Okay. Okay. All right, so we got these molecules moving, right? Moving around. And I'm gonna put on, this is like a pot of water. And I'm gonna turn on the Bunsen burner in the middle, right? And what's gonna happen? What's gonna happen to this pot of water? You guys ever make spaghetti? Anybody ever cook spaghetti at
Oh,
home?
bubble up.
It bubbles up, right?
Yep.
So the water starts to heat, right, and rise. And what does the hot water do? Because the water is going to start heating down here by the Bunsen burner. And then once that water, it heats, it gets less dense. So what happens?
It goes to the
Rises.
surface.
So the warm water is going to start here, but because it's less dense, it's going to move up. So it's going to get a convection current pulling it to the top. Right, so the hot molecules are going to leave here and move up here. What's that going to do? That's going to make a vacuum or a less dense area, so new molecules will flow in. Cold molecules will come in, they'll get heated, they'll rise, right? And I get this current going. Everyone know what I'm talking about?
That's why we have the AC in the ceiling, right? Because the cool air goes down, the hot air goes
Yeah,
up.
I mean, that's the best way to do it. Yeah. There they go. They went up, right? And new molecules come in, and you can see I'm getting this current flow, right? This is a convection current, right? I'm transporting hot molecules from one location to a new location. Okay, make sense? All right. Luckily, you only have to know the definition of this. We're not going to calculate with it. Isn't that sad? So it's a little more involved, the mathematics of this. So we're going to go on to the last one, radiation. Okay? Radiation is not like the Hulk, or it's not like going to give you cancer. We don't mean that kind of radiation. We mean electromagnetic waves. Right? So, in that sense, there's radiation all around us, right? All the light coming to us is what I'm talking about, that kind of EM wave. Right? So, radiation is giving off EM, electromagnetic waves. Right? Electric magnetic fields. We're going to talk about that later in the semester. But, so let's imagine we have an object. Let's do it in blue. Blue and that. Right, here's my object. T. Give it a temperature T. And then so look at the environment here. TE is the environment temperature. So this object sitting in the environment. Let's take my cup as an example. Right? It's sitting in the environment. It's going to be giving off electromagnetic radiation. Right, so it's giving off waves here. And for simplicity, we're going to start with T, the object, greater than the environment, just to begin. So here comes these electromagnetic waves. They're going all out into space. But of course, it's going to absorb light too, coming in. It's just less light's coming in than going out because it's hotter. So in comes environment electromagnetic radiation. Okay? And the formula for this is interesting. The power, right, of transferred energy is equal to sigma. That's called the Boltzmann constant. We'll write that down in a minute. Another constant, E. This is a constant in nature. E is a constant in material. It's called the emissivity. Well, look at that. A is across the total area of the object. And then temperature of the object to the fourth minus temperature of the environment to the fourth. Right? It's giving off energy, but it's absorbing energy. And so that's why there's a difference here. So sigma is called the Boltzmann constant. And its value is, I have it on my notes because I don't have it memorized. Sigma equals 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the fourth. Okay, it's one of these constants in nature.
What about E? Is it the Euler's formula?
No, E is not Euler's. E is called the emissivity. Can't spell, so it's something like that. This depends on the material. So what do we mean by that? Okay, let's think July. Yes, question?
Do we need to know the Boltzmann constant?
You don't have to have it memorized. I'll give it to you if you need it. Let's think July, Florida, high noon. You go outside. Do you wear a black hoodie? No, why?
Absorbs energy.
It absorbs all the heat, right? So things that are really black, like usually the example given is a cast iron pot, right? Because they're really black. The emissivity is close to 1. It's a dimensionless constant, but it depends on the material. So something really dark is going to have a high emissivity, high being close to 1. Right? What do you want to wear when you go outside in July, in Florida, in the summer at high noon? What color do you want to wear?
White.
White, because it reflects, right? It doesn't absorb. So the lighter the color, the more it's going to reflect, the less emissivity. The closest you can get to 0 would be silver mirroring. Like you could take a nice mirror outside, right? It's going to reflect the light, right? All of it. So this is close to 0. So that's our range from 0 to 1 for the material. Okay. Now most objects that are warm, I'm talking body temperature, room temperature, they're giving off radiation in the infrared spectrum. And so I brought an infrared camera so we can see that. So this is pretty cool. So I'll pass this around for you guys to see. But this camera measures infrared light, right, instead of visible light, like what we're seeing. And so it's looking for the heat of an object. So right now, if you pass this around, you can see my water cup. I filled it with hot water before lecture. And so look at the water cup, aiming at that.
You gotta aim it.
You gotta aim it, and what do you see? It's different than the environment, right? Pass it around. You see it's nice and bright, right? That's because I put hot water in the cup. Does that make sense to you guys? I'm looking at your hand.
Yeah.
Keep going, let everybody see. You can look at your cups and stuff, but I want you to see the water to start. Right? You can see the water there. You can see me.
Your brain is very warm.
Yes, because I'm a genius. But glass is blocked, right? If you look at my face,
Yeah.
the glass is blocked. They block infrared. They're not visible through, but they're blocking infrared light.
So does it measure like the thermal, like the heat?
It's measuring the wavelength of light coming off in the infrared region. That tells you how hot the object is.
And how do you do those? Like what's
What do you mean?
What's the technology that you need to do those?
It's the same as a camera. You're just looking at a different frequency instead of visible spectrum. You're looking at infrared spectrum, a little bit longer wavelength. But it's just a photo detector. just
So an
like-
iPhone could do that as well.
Probably, depending on if that detector in there can pick up infrared. I'm not sure it can. If it could, then you could. Yeah, depending on the detector to measure the light. Right? Okay, you got it? You saw the cup? Now, check this out. Keep looking.
Okay.
Here's the cup, right?
Yeah.
Look at the table. Look at the table.
Oh.
Do you see the spot on the table?
Yeah.
Why is that spot showing up? The cup's over here. But what does the cup do? It transfers heat, right? How did the heat, conduction. It transferred heat from the cup to the table by conduction. So that spot on the table is still warm.
Yeah.
Right? You can pass it around. You can see. It looks like you can't tell there's a warm spot here, looking at it. But there's a warm spot on the table. Right? Does that make sense to everybody?
Is there a warm water in the cup?
Yeah, I put hot water in the cup. So I filled it, like with the tea maker.
Dr. Brown, if you have two masses, same area, one is 100 Celsius and the other one is 0, does it mean that the temperature that is going to be the thermoequilibrium is gonna be like a 50.
If
flat.
they're if they have the same mass and the same specific heat, or that different specific heat's gonna be different. You can look at electronics too. You know, like the computer's giving off heat, right? You see it. You know.
Oh, this one is really.
Yeah, it's going. I bet your iPad. Look at her tablet. Is it giving off heat?
Not that much.
Yeah, it's probably because it's not a. It's a.
Not even
It's
close.
a Kindle.
A Kindle, right? So it's not. It's not a glass
Yeah,
screen.
mine
it's
is.
that-
Your phone is a lot.
Yeah, because I'm recording and it's a color screen. That's like ink paper, so it's not as bad.
Hers is almost 0.
So,
Yeah.
is your phone giving off any energy?
Oh no.
What happens if you take that outside in like 90 degrees?
It would probably see everything. I mean, I don't know how well it can pick up then the background difference, because the environment's going to be, you know, in the similar temperature range.
What's the button for?
I think take a picture. It's got a. You can put a memory card in and take pictures, download it.
Awesome.
Alrighty, that's all I got for today. I'll let you go early. Today in lab we're doing thermal expansion, so I'll see you there.
Perfect.
And
Is it a worksheet today or your packet?
yeah, it's online. I'll also bring a printing copy.
Okay.
You want to kill the recording?
Yeah.